This video is over topic 31, numbers 4 and 5. So on these, we're given exponential functions. We're going to analyze a little bit about what the pieces of the function mean, as well as practice calculating with those functions. So number 4, the function p of t equals 57,040 times 1.023 to the t power. T equals years since 2010. The whole function can be used to model the population of Northport, Florida. So what was the population of Northport, Florida in the year 2010? T is years since 2010. In the year 2010 would be T equals 0, or in other words, that would be at the start, meaning we are looking for the initial value. It's the 57,040, no calculation needed. All right, does this model represent growth or decay? Growth or decay has nothing to do with the initial value. It has to do with what's there in the parentheses, the thing that's being raised to the t power, the growth factor, or the change factor in this case. The change factor is 1.023. One way to think of it is this 1 plus something, or is it 1 minus something? And in this case, to get to 1.023, something got added. So it's this one. That means it is growth. By what percent does the population change each year? Now we're looking at, all right, what was it that got added? What got added to 1? So 1.023 is 1 plus 0.023. The 0.023 convert to percent form, 2.3%. And here, because it asks change, then this is increase, we'll leave it positive. If it was decrease, we would put it as a negative. All right, then use the model to predict the population in 2027. We need to know what t is. So t, looking at t years since 2010. So 2027 is how many years since 2010? You can do a subtraction if you need to. 2027 minus 2010 is 17. So you get t equals 17. So plugging in 17 for t, 57,040 times 1.023 to the 17th power. And make sure whatever calculator you are using that you can do this calculation correctly. You're not going to multiply the 57,040 by 1.023 and hit equals, right? That is the order of operation. The power gets applied to the 1.023 only. So order of operation, if you're doing it one step at a time, would first be the 1.023 to the 17th power, then multiply by 57,040. But you should be able to do it all in one entry into the calculator, and the calculator will apply correct order of operations. So make sure you can get 83,958.619, etc. And that rounds to 83,959. Then number 5, a factory left a small town and the people started to leave also. The population of the town t years later is represented by the function p of t equals 9,800 times 0.07 to the t power. So what was the population when the factory closed? It's t years later, referring back to the factory left. That was the starting point. So when it says when the factory closed, it's looking at the start. And that's going to be this part of the equation, the 9,800. All right, does this model represent growth or decay? We need to look at the 0.7, the change factor is 0.7. Is that 1 plus something, or is it 1 minus something? Well, to get to 0.7 from 1, you have to subtract. So that means it is decay. By what percent does it change each year? What got subtracted from 1? So 1 minus what gets to 0.7? If you need to, you can rearrange that and say this is 1 minus 0.7 equals that unknown value. So that would be 0.3. And that is 30%, not 3%. 0.3 is 0.30, not 0.03. So 30%, and because it just said change, we'll put a minus on there. So it is decreasing by 30% each year. All right, what was the population 3 years after the factory left? Plug in 3 for T, 9,800 times 0.7 to the third power. 3361. And then 10 years after the factory left, 9,800 times 0.7 to the 10th power. 277.